keep in mind this is a constant pressure process. So that means pressure is not changing. Here we have a piston cylinder device. So initially it contains 1.5 kg of liquid water. So that's actually the mass. And the pressure and the temperature is given 150 kPa and 20 degrees centigrade, that you can see from here. So water is now then heated at constant pressure. The pressure is 150 by the addition of 4000 kilojoule of heat. So we are applying the heat. So this is heat in. So here this is actually the heat in, right? This is the mass, and this is the pressure, this is the temperature, right? What we need to do is we need to actually determine the entropy change of the water during this process. So here you can see, guys, this is actually the T and the S diagram. TS diagram. It's clearly showing the phase change. So here we can say this is the initial phase, this is the final phase. We know actually the entropy changes delta S. We can say the entropy change for the final phase and the initial phase, the entropy difference between final and the initial phase. So for initial phase we said the entropy is S1, for final phase it is S2. We actually need to calculate delta S, so the difference between these two, delta S, and we know the formula delta S, it is equal the M S2 minus S1, right? So that means we need S2 and S1. We already know M. So in order to calculate this entropy S2 and S1, S2 for the final phase, so if we want to calculate the S2 entropy, then we actually need any two properties, because if we want to calculate from the table, so let's say we know already the pressure, so we know the pressure, so we need either the temperature or we can say the H2, the enthalpy. If we get any two properties, then we can get the other one. For phase 1 or the initial phase, we know pressure and temperature, so we can easily calculate S1 by using P1 and T1 from table S6. So this is actually the total process. We will calculate S1 at first, then S2, and then we will get the entropy changes, right? So this is actually you can say the overall flowchart we're going to follow. So now we start with this, the solutions. So here we will write down some assumptions. So the assumptions is, here we will say that okay, we have this piston cylinder device. So inside the cylinder, what we have the water, H2O, that is the water. It is not moving. It is a stationary object. So as it is the stationary object, so the kinetic and the potential energy, it will be zero. So the first assumption is the change of kinetic energy and the change of the potential energy, it is equal to zero. That's what we said. We can say it is a quasi-equilibrium state. So quasi-equilibrium, yeah. The process is quasi-equilibrium, and pressure is constant. So it is a constant pressure problem. So for the initial phase, pressure is given P1. So for initial phase and the final phase, pressure is constant. So P1 and P2, it will be equal, right? Correct. So it will not change. So now we will start with the analysis. Look, when we will start with the analysis, if we consider this is the system, then you can see we can consider this is a closed system, because no mass is crosses the boundary, the system boundary, during the phase change process. So no mass is crossing the boundary, so we can say it is a closed system. And when it is a closed system, you see we have the piston. So in this piston cylinder device, actually it involves some moving boundary. So this piston will move, so we have some moving boundary, so we have some boundary work. So that's actually the boundary work we have, and the other work is you see this is the work the heat, that we have the heat energy here, the Q in, and we have the moving boundary, so we have some boundary work WB. So I can write it as that we have the WB, the boundary work, and we have the energy in. Right, so the first, what we'll do, we'll calculate S1. So that's our ultimate target. We need S1 and S2. So what I said, we can calculate this entropy by using these two properties, P1 and T1. So if I start with these two properties, P1 and T1, so let me write it down when it is state 1. Okay, so before going to calculate that, we need to understand something else. Here you can guys see the temperature is 20 degrees centigrade, right? At 20 degrees centigrade temperature, from the table, the saturated water table, we know the saturation pressure is for T1 equal 20 degrees centigrade. The saturation pressure is 2.3392 kPa. So it is actually the saturation pressure, right? Here you can see for the initial stage we have the pressure 155, which is greater than the saturation pressure at this point. You know what I mean? So according to the theory, the property table, as the initial state pressure is 20, so saturation should start at this pressure, but we see this is at 150 kPa. So that what it means, it is actually the greater than the saturation pressure. So we can say that water exists as a compressed liquid at initial state, since the pressure is greater than the saturation pressure. So what we can approximate here, as it is greater than the saturation pressure, so we can approximate the compressed liquid as a saturated liquid. So our assumption here is compressed liquid as saturated liquid. Okay, so that we just approximate at given temperature, which is 20 degrees centigrade. So what I said, guys, as the water exists as compressed liquid at the initial state, as you know, the pressure is greater than the saturation pressure at 20 degrees centigrade, so we approximate the compressed liquid as saturated liquid at 20 degrees centigrade. So for state 1, we know the pressure P1, it is equal 150 kPa, and T1, it is equal 20 degrees centigrade. So for this P1, in this case, we will actually use the table A4. I'm not showing you the table here, table A4, because this is you are using this table. You already learned actually how to use all these property tables. So it will be kind of like this. We can say the entropy S1, it will be, we can say SF, that means the saturated liquid at 20 degrees centigrade, it will be 0.2965, and the unit is kg joule, kg per Kelvin. And when so we got the S1, that means what it is, the entropy. And if we calculate the Haze on the enthalpy at the same temperature, so we can say Haze F at 20 degrees centigrade, it will be actually 83.915 kilojoule per kg. So this is actually the two properties. Here, guys, look carefully. If you go back, we actually need S1 and S2. So here we calculated S1 from table A4, and we also calculated the Haze on the enthalpy. We actually need it, and then that I will explain gradually. So S1 is we already got. So now for final state, state 2. So for state 2, what we know according to the assumption it is a constant pressure process. We said P1 and P2 they are equal. Pressure will not change. So that means we know it is also equal to P2. So we know the pressure P2 equal 150 kPa. That's only one variable we know. But we need S2. So if we want to use the table, then we need at least one more properties, right? Otherwise we can't calculate the entropy S2. We need S2. So we know only the pressure, so we need one more property. So what we can do, guys, we can calculate Hayes 2, as we got Hayes 1 from this table A4 for initial state. So if we can calculate Hayes 2, then by using this pressure and the enthalpy, we can get the entropy, right? So what we can do, guys, here we can do the energy balance, because the energy balance, what we can see here, the the Q energy in, we have the the moving boundary work, right? So and definitely the internal energy it will be like the enthalpy here. We know the definition that I will show you clearly. So now let me show you the energy balance. So energy balance formula, we know the energy in, the energy out, it will be the energy change inside the system. So here, what is the energy in? Q in. Okay, right, it is Q in. What is going out? The boundary work, WB. And inside this, what is we say, and the delta E, it will be actually the change of the internal energy, delta U. I believe you understand. So here we can say this Q in, it is equal delta U and WB. If you can remember, we said it is a constant pressure problem, and we had another the assumption it is quasi-equilibrium process. So for constant equilibrium, quasi-equilibrium process, this delta U and WB, we can say it is actually change of enthalpy, delta Hayes. That's some combination property we discussed a couple of weeks back, delta Hayes. So that means this expression now becomes Q in, it is equal delta Hayes. And the enthalpy, delta enthalpy change is the M Hayes 2 minus Hayes 1. Delta Hayes, we can say it is equal Hayes 2 minus Hayes 1, and we have the mass, specific mass, so M Hayes 2 and Hayes 1. So that what we can write, guys, here, this Q in, it is equal M Hayes 2 minus Hayes 1. So look here, we know this Q in, what it is given in the question, 4000 kilojoule, M 1.5 kg. What is Hayes 2? Hayes 2 we need. I showed you here. If we get Hayes 2, then by using this P2 and Hayes 2, we will get S2. So Hayes 2 is unknown, we are looking for, and the Hayes 1, you can see from the previous one, it is 83.915. So I should say 83.915 kilojoule per kg. So if we simplify this, we will get Hayes 2, it is equal 2750.6 kilojoule per kg. So that means we got Hayes 2, and we know P2, it is equal 150 kPa. So now we are looking for S2 by using these two properties here, this Hayes 2 and P2, right? So we need to use the table A6, because the final stage, you can see it is actually a superheated region. So table A6, this is for the superheated properties. So what we can write here, guys, P2, it is equal 150 kPa, and Hayes 2, it is equal 2750.6 kilojoule per kg. This question is little bit lengthy. We need S2. So what I said, table A6. we are going to use table A6, and we need to do some interpolations, guys. Keep in mind it is 150 kPa, so that means we can say it is 0.15 MPa, right? If you look from table A6, we have actually 0.1 MPa, 0.2 MPa, so we have no information for 0.15 MPa. So that makes our life complicated. And H2 is this, so that means we need to do 3 interpolations here to save some of our time and avoid, we actually want to minimize the time, actually the video, the length of the video. So here you can see we need to do 1 interpolations for this 0.01. we need to do 1 interpolations for this one, and once we have done this 2, then we need to do another interpolations between this 1 and 2, and that will give us the in the S2, the entropy for the final phase. Here I will quickly show you, but I will not do whole process because you know how to do the interpolations. 0.41 MPa, if you see what is the H2, 2750.6. so here it is the enthalpy, so our value is 2760, okay, 2750.6. so it should be somewhere yeah, so you can see 50.6, so it should be here in between these two value, right? So look, these two, this is 26.75 and it is 27.76. so now what we will do, guys, we will actually use this two value, and so keep in mind it is 2670.8 and 27.76.6. okay, so let me write it down here quickly. So it is, oops, yeah, so it should be 25.8, and for this we got it is 7.3611, and our ultimate value is 2750.6. we are looking for this value. Instead of x, let's say it is s, and the final on what it is 27.76.6, and it will be 7.6148. so if we do this interpolation, so this is first interpolation, guys, and from this interpolations you see we will get s, that means the entropy for this value. So it will be it could be I'm telling it could be kind of 7.5492 or something like this. This calculation is not 100% appropriate. And now, and this is for, you see, 100 kPa. okay, and now we need to do another interpolations for, this is 0.2 MPa, that means 200 kPa. And here again, if we use the values from here, so let me just write it down clearly. For 200 kPa, the values, it will be something like this, 2706.3, and for this value enthalpy is 7.1270, and this is 2750.6. let's say this is s again, and the final is 2769.1. it will be 7.2810. so we need to do another interpolations for this, and you see here for this 200 kPa we'll get, let's say the entropy is 7.2356 or something like this. So now what do we need to do, guys? So for 100 kPa we got this value, for 200 kPa we got this is the entropy. Now we need the values for 150. So if I write it down here, for 100 kPa the value is, let's say, 7.454927. For 150 kPa we are looking for this S2, and for 200 kPa we got it is 7.2356. So if we do all of this integration interpolations again, so the values of the S2 here, this S2 will get it is 7.3674 kilojoule per kg Kelvin. So look, this is a lengthy calculation, interpolation. So if you get this sort of question in the final exam, then we'll provide necessary information, and you do not need a lot of interpolations. That will when I will prepare the final exam question, then I will take care of this issue, that and then you do not need to do a lot of calculations. So we got S2 here. Now you see delta S, we know the formula M, S2 minus S1. So M is 1.5, S2 is 7.3674, and S1 is 0.2965. So it will be 10.61 kilojoule per kg. So this is actually the entropy change. The overall question, it is pretty straightforward, but it makes our life complicated when we actually wanted to calculate the the entropy for the final phase here, especially when we wanted to calculate the entropy here. So I think you understand, guys, and we'll discuss this problem during the lecture again. Yeah, so that's it.